Hello physics students. Today we're going to be talking about something called free fall. But before we do that, I just want to review what we learned about kinematics so far. So remember, kinematics is the mathematical or the numerical study of motion. It's like creating a formula or a numerical record of something moving with numbers. So in the topic of kinematics, there are three main ideas. The displacement is the net motion of something, the meters, how far it is from its starting point. The velocity is how fast something is going, including its direction. And acceleration is how quickly something is speeding up or slowing down or turning. All these terms are vectors. And in our case, that means that they can be either positive or negative to indicate the direction, because we're kind of stuck like on one dimension, like an x-axis, or maybe like a railroad track, forward, backward. So if something is moving, for example, with a velocity in the forward direction, we would say that's positive, and with something moving in the backwards direction, we would make that velocity negative. And so that's how we would factor in the direction or the vector nature of something is with pluses or minuses in the problems we're solving. Acceleration could also be positive or negative. And remember, the important thing there to understand about acceleration is that positive acceleration doesn't mean the object is always speeding up, and negative doesn't mean it's always slowing down. The key idea is if the object has the same sign for acceleration and velocity, positive, positive, or negative, negative, then the object is speeding up, because the acceleration, the gain, is the same as what you already have. For example, you might have a negative backward velocity. A negative acceleration means you're getting more of that backwards velocity. You're speeding up with a negative acceleration. And the way something slows down is when the acceleration and velocity have opposite signs. So maybe the acceleration is negative and the velocity is positive, slowing down. But the acceleration could be positive, and if the velocity is negative, that's also slowing down. Okay, so those are the kind of concepts that we studied with kinematics so far. Today we're going to take them into objects falling. Now the first point I want to make is when people hear falling, they typically think of this, right? Something going down because of gravity, the force of gravity. But in our studies, falling is also this. While this ball is rising, we say in physics it's in the state of free fall, meaning there are no other forces but gravity acting on the object, okay? Technically that's not true. There's always around the Earth a little air resistance, so we're not going to be studying things like feathers dropping. We're going to be studying things in the presence of air that have a sufficient density so that the air resistance is not a significant factor. We could ignore it. Okay, so the first thing that we're going to do is we're going to look at just the concepts of free fall. So what I have here is a diagram. Before I pause to let you copy it down, I want to just make some points here. These velocities, the subscripts indicate the time at which they were recorded. This is at time 0 when an experiment began, 1 second, 2 seconds, 3, 4, 5, 6. The other thing I want to point out is I'm launching something off the ground with positive 39.2, so the positive sign is indicating the upward direction. Notice the arrow is very long here because we're moving fastest, and then the arrow gets progressively shorter and there's no velocity here. Then this arrow is the same as that one, this one the same as that one, this one is... So those are the key things I want you to sketch in your diagram. So I'll pause the video now to give you an opportunity to jot this down. Okay, so next what we're going to do is summarize the concepts that are embedded in this diagram. Because the hard thing about free fall is there's a lot of concepts that you have to know. The problem will not tell you information. You have to know it in your mind that when something is falling, these things are true. What are the things? Okay, so I'll pause to give you a chance to jot this down. Okay, now the concepts. The acceleration is constant the entire time the object is in that state of free fall. That means the acceleration on the way up is negative 9.8. On the way down, it's negative 9.8. And at the peak, it's negative 9.8. Let me talk about that for a while. Because a lot of students, again, they get rooted in that idea. Negative acceleration means slowing down, positive means speeding up. So when they think of something rising, they say, okay, that's negative acceleration because when I throw something up, it's slowing down because of the action of gravity in the downward direction on the way up. So negative 9.8 on the way up. But then when it starts going downward, they say, oh, now that's speeding up. That's going to be positive acceleration. Negative 9.8, positive 9.8. Not true. If you look, remember, acceleration is how the velocity changes every second. If you look from 1 second to another, what am I adding to 19.6, to 39.2 to get to 19.6? I have to add negative 9.8. How do I get to 9.8 if I started at 19.6 velocity? I have to add negative 9.8. How do I get to 0 starting at 9.8? I have to add negative 9.8. All right, good. So negative 9.8 on the way up, slowing down. But then ask yourself, if I'm starting at 0 velocity and then I start going downward, so right, velocity is a vector. When it's going up, I call that positive. Well, down, I've got to call that velocity now negative because it's going down. So how do I get from 0 to negative 9.8 velocity? I have to add, once again, negative 9.8. How do I get from here to here? Once again, I have to add negative 9.8, have to add negative 9.8. Negative 9.8 the whole time. The other thing that students mess up is they'll say the acceleration at the peak is 0. That is not true. The velocity is 0, and it's easy to get the two confused. But remember, acceleration is speeding up, slowing down, or turning. If you have 0 acceleration, that means you're doing none of those things. You're neither speeding up, you're not slowing down, and you're not turning. So if I launch a tennis ball, and then it gets to the peak, and it has 0 acceleration when its velocity is 0, that means it's no longer speeding up, slowing down, or turning. That means it gets to 0 velocity, and the velocity stays 0. So if the acceleration was 0 at the peak, we'd always throw something up and then the object would hover there forever. Never happens, right? The velocity is 0. Velocity is 0. And then a split second later, the velocity changed. So that changing velocity is acceleration. Even though it was 0, it changed right away. That's acceleration still, okay? So key idea, always negative 9.8, or you could say downward 9.8. You could say the negative sign with a word. The other key point is the velocity at the peak is 0, but the acceleration is not. I just explained that. And then the object returns to the same altitude with the same speed. Notice if I look at this altitude right here, when it's passing, it passes with positive 19.6 velocity. When it comes back, the speed is the same, but the direction changed, so it just has a minus sign in front of the number now. So that's how I write that mathematically. V final is the negative of the V initial. In other words, when we had 19.6 at this altitude, the final is negative 19.6. And then the other key idea is that the time on the way up is 3 seconds in this case. 1, 2, 3. The time on the way down is 1, 2, 3. So the object spends the same amount of time on the way up as it does on the way down, and that's half the total. So 6 seconds in the air, 3 on the way up, 3 on the way down. Those are the ideas that you have to know. The problems don't tell you, and that's what makes free fall calculations often a little tricky. Sometimes people find that difficult. And I'll explain with an example. So give me a second. So let's take a look at our first example. Okay, so a student drops a penny 0.5 meters above a table. How long does it take to land? All right, so that's the difficult thing with these free fall problems. Very often they just give you one piece of information and you have to know the rest. So the first thing that we learned or we know is that the displacement is it's going to fall down 0.5 meters. So that's down 0.5 meters, right? I drop something, it falls down, right? We call that negative. And that's it. But here are some key words. Drops. When I drop something, I'm going like this and then I open my fingers, right? I do not go like that. I don't throw it down, I drop it, right? So that word drop implies V initial equaling 0, okay? So the other thing is we're dropping a penny. We're assuming air resistance is negligible. The problem didn't tell us. We need to know acceleration's negative 9.8. Well, you know, you don't have to remember the number 9.8. Remember that on the front cover of the reference table, right here, right, you see G equals 9.81. So you don't have to remember the number, but you have to know that it's on the reference table. You could look up, and it's in the downward direction. We'll call negative 9.8 meters seconds squared. It doesn't go up into the sky. It pulls it down to downward, okay? And how long does it take to land? T is what we're looking for. All right, so we have to go to the reference table and find the appropriate formula now, okay? See, once we lay this out, we look for a formula with those variables, and if we go to the back of the reference table right here, let me wait for the focus. So you see that the formula that includes d, vi, t, and acceleration in time is this one right here by my finger. So, and again, so the other thing is since vi is 0, we could leave that part of the formula off and just write the formula as d equals 1/2 at squared, and that's full credit. We don't lose any points for that. So that's what I'm going to do is begin with d equals 1/2 at squared. Okay? So now I have to plug in the numbers that I sort of pulled out of the problem and from what I understand free fall. Negative 0.5 meters equals 1/2 negative 9.8 Just want to point out one common mistake students very often make. They do 9.8 meters per second, and unfortunately that becomes a 1 out of 2 on the Regents. You have incorrect units. Can you imagine solving all this, knowing all this, solving the problem out, leaving that little square off and you get half credit? Terrible, right? Terrible. But we have to know that so we're prepared for that crazy grading scheme. All right, if I divide both sides by negative 4.9, which is what, 1/2 of 9.8 is, then what I have on this side is t squared. And on this side, I believe it's 1.02. Okay. And then I have to square root both sides. And that comes out to be maybe like 0.31 or something like that. Well, I could get my calculator, but I think it's something like that. 0.31 seconds. Okay. So again, lay out the formulas, the variables, find the formula, plug and solve. But a lot of these you have to know from that diagram that I erased. Let's take a look. Oh yeah, I don't remember if I paused the video. So let me pause now for you to get a chance to jot that down. All right, let's take a look at a second example. So again, only one piece of information given in this problem. How fast must a clown launch a juggling pin for it to rise exactly 2 meters? So we have to once again write down all the information that we are given plus what we know about free fall and then look for a formula. So this is, sorry, I meant to mention this about this problem. If you did this, you're welcome to leave off the minus signs in a gravity calculation, and you won't lose credit and you won't get the wrong answer. You'll get the right answer. The only time where you really have to be strict with minus signs is not if something's falling straight down, but if it's rising. Then you have to be very careful with minus signs because we have velocities and accelerations in opposite signs. So if we call, when something falls like this negative and negative, we're consistent. If we call this positive displacement and positive acceleration, we're consistent. They're both in the same direction. But if we call this positive velocity and this positive acceleration, now we're inconsistent in our problem. So be careful. When something is rising at any point in the problem, you have to be very strict with this being negative and that being positive. Not important in this problem, but in this one it will be because the clown is throwing this up. So we know that the upward displacement now, we're going to call that positive 2 meters. And that's all that's given. But remember, we know that this pin is under the influence of the Earth's gravitational pull. So the acceleration now is negative 9.8 meters second squared again, but we now have to have opposite signs for those. Very critical. Okay, and then the other thing is we want to know how far, when it rises exactly 2 meters. So what we're looking for is, I'll leave a space here because we know one other thing, but what we're looking for is the velocity of launch. The V initial, right? The clown's going to throw that up in the beginning. So that's what we're looking for, how fast when you throw it up in the beginning. But the other piece of information that we also know is that when something is launched like this with the V initial, and then it gets to its peak, where it gets to the final point up here, we know something up there, and that's the velocity. That at that moment, we know at the peak, the final velocity, after the motion we're investigating, is 0. Okay? Again, that's what makes these problems very difficult, is that we are only told one thing, all the other stuff we've got to figure out from our understanding of how things are in free fall. So let's look for a formula with those variables, the two velocities, acceleration and displacement. So if I go to my reference table here, you will see that the top one doesn't have any displacement in it. This has displacement, but time, and we don't have time. Finally, this is the one that we need to use, the two velocities and acceleration and displacement. So let me write down the formula. There. And then I'm going to plug in 0 here. That's the final velocity. I'm looking for the V initial. The acceleration is negative 9.8. And the displacement is a positive upward 2 meters. So what I'm going to do is now this multiplied all out is negative 39.2. If you do that on a calculator, punch it all out. So I'm solving for this. I've got to move this to the other side by adding 39.2. And when you take 0 and add 39.2, you get 39.2 equals V squared. I didn't mention this, but I should have on the previous problem too, is that in this step you need all your units. In this one, on the Regents, you don't need the units in the intermediate steps. You need them on the answer. So when I take the square root of both sides, Then I finally get my VI that the clown has to launch us up at, and I think it comes out to be 6.3. And I need my units here, okay? Otherwise 1 out of 2. So there's the solution. Lay out the variables. This was the only one given. The rest we had to piece together from our understanding from the first diagram I had on the notes today. And then we look for a formula, plug in the numbers, and get the answer. Okay? Now, I don't want to make this video too long, but let me just set up another example, because this one I think, I don't know if I pause. So let me pause here and allow you to jot these notes down. Okay, so one more example. I'm just going to set it up. Clown launches pin at 5.2 meters per second. How long does Okay, so the clown launches the pin up at 5.2 meters per second, and now we're asking, how long does it take to come back to his hand? So I throw it up like this, the pin's going to go up and then come back to his hand. And how long? So how long is basically the time that we're looking for. So what's the information given? The only thing, once again, is the one number, the VI. But we know that acceleration for that pin is going to be 9.8. But in this case, once again, this is a problem where something is rising and then falling. So we have to be extremely strict with the signs here. So if I'm going to call upward positive, because that's what the clown's doing launching, then the acceleration being down, I need a minus sign. Okay? And then the other thing is we're looking for the time, how long. But the other thing that you have to know from launching problems is that if you launch something up, when it comes back down, it comes back with the same speed, but the direction has reversed. So we actually know V final is negative 5.2. Okay? So if we look for a formula, the formula is V final equals V initial plus AT. So the final is negative 5.2. The initial is positive 5.2. And negative 9.8 is the acceleration, and time is the unknown. And we solve for the unknown. So that's free fall, okay? So again, we learned a bunch of concepts about how the velocities, accelerations, and displacements change when something is thrown up and goes up and down. And then we did a few example problems, because the problems in this case usually just give one number. The rest of the numbers you have to piece together from your understanding of that first diagram that I drew. All right, so that's it for today. I'll see you in the next physics video.